So next one is we have Mark Larson, who works in Chicago, working on the US Muon Collider. And he's going to tell us a few bits about that collaboration emerging of cross figures for the future.
Yes, so I'm a physics PhD student at Chicago, and indeed I'll be talking about some of the computing requirements and challenges we've run into so far for our relatively new collaboration with the US Muon Collider community, as well as the international Muon Collider collaboration. Okay, so you may or may not have heard of the concept for building the Muon Collider. And I guess unlike some of the other talks today, this is not a currently actively known thing, but rather proposal to be the next high energy collider after the high luminosity LHC. So there are a few reasons why we want to build a Muon Collider. Ultimately, this provides a really unique opportunity, also challenges in terms of building the next high energy collider. This comes from a few properties of muons, the fact that they're more massive than electrons. This allows us to reach the higher collision energies that we want to sort of push the next boundaries of physics. They're also fundamental particles, so you get cleaner collisions compared to, for example, LHC or reflected protons. However, where the challenges come in is the fact that muon is unstable, it's very quickly. So this poses issues both on the accelerator physics side of things to try to accelerate the muon to high enough energy quick enough before it decays, and also as we'll see on the detector side of things, and in sort of initial simulation work. And additionally, I'll mention that another benefit of building Muon Collider is that it's significantly more compact than, for example, the future circular collider that's being proposed. So you can actually fit the entire machine within the Fermilab site, which would also provide an opportunity to bring back collider to US. But so the actual idea of what the Muon Collider looks like, we have some muon injector. I don't want to go into the details of, but this feeds into an accelerator ring. We accelerate these to 20 center mass energy. These are then injected into a about 10 kilometer circumference collider ring. And then there would be a plan to have two interaction points, so to experience eventually. So as I mentioned, because the muon is unstable, we deal with some significant challenges. And the main challenge that's we're dealing with both from the detector design point of view, but also in our computing in terms of what we're trying to simulate currently, is from what we call induced background. So the fact that the muon is unstable, we have that a lot of the actual muons in our beam will decay, especially close to our interaction points. So to mitigate these high energy electrons neutrinos that we have, we place this tungsten nozzle near the interaction points to sort of shield the detector from radiation. And so while this does absorb much of energy that we're dealing with, it still results in this huge shower of low energy particles. So you can see here a sort of event display of a single beam beyond decay. You can see the many neutrons, photons, to a lesser extent, positrons and electrons that are from the interaction of the decay products with this tungsten nozzle. So this is the depiction of just one decay. However, for each one crossing, we have about 10 to the 5th muon decays per meter here. So you can imagine multiplying this by 10 to the 5th, you have a very, very complicated sort of event. And so this results in roughly 10 to the 8th beam induced background particles per event. So you can hopefully start to see the issue in simulating this at this stage, in addition to the issue with development. So the ultimate goal of the simulations we're doing right now is to demonstrate that we can efficiently reconstruct physics objects that can be used for analyses in the presence of all of these beam induced background particles. Okay, so I'll give a brief overview of the simulation workflow that we're actually working with. So it starts with doing some sort of color generation of both some signal that you're interested in trying to reconstruct. So simulating your muon collisions and what they produce, as well as the generation of your beam induced background particles from some number of decays happening from the material. Both of these are then separately sent to the next stage of the workflow, which is actually simulating interaction that's our true bubble particles have with the detector itself. And this uses tools like JM4 and after this, we take what we'll call hits, or just places that the particles interacting with the detector, and effectively overlay the signal and use background hits at the top of each other. Next, we use a digitization step in which we actually take into account the properties of the front-end electronics, taking into account uncertainties and things of our readouts. But also this step, we apply some sort of front-end double cuts. So for example, we apply a timing window, so we'll be reading out the detector around some timing window around bunch crossing. And this can significantly reduce the number of images backgrounds we're dealing with. And then finally, that's fed into reconstruction algorithms. And the goal here being to construct high-level physics objects, such as tracks, for example. This is using some third-party tools, such as VCPS, common tracking software, which is meant to be an experiment-independent toolkit for constructing tracks, as well as Pandora for particle flow to actually construct which particles we're seeing. But as you can imagine, providing so many beam-reduced background hits, these complex reconstruction algorithms. So, okay, so we're given an overview of some of the sort of benchmarks that we're dealing with in terms of first CPU time. So simulating one beam-reduced background event with all the hits takes up to around 24 hours per event. And this is significantly longer than it takes to simulate just the signal process, which is around just 10 minutes per event. For the overlaying step, it takes only about 5 minutes per event. However, because we're dealing with very large files each time, this can be very IO intensive for us. For running the full reconstruction of the full detector with sort of the benchmark algorithms, and with all of your big hits, this can take around a day per event. So it's both very CPU intensive and it's quite a long time. In terms of memory consumption, throughout the entire simulation workflow, we observe only getting up to around 32 gigabytes when you're processing a single event. However, we find that when you submit jobs with just one event, this is sort of increasing steadily. And additionally, when we test more advanced reconstruction algorithms, it's sort of my experience in the study that's Chicago has worked on, we find that this can increase very, very significantly.
Is it working for all? With the policy purposes for down. This is just one case or both?
So this is the case of the benchmarks that were published.
Okay, I see.
So our study is doing something separate, which because ultimately we're dealing with more like 40 to 48 gigabytes using just 10% big overlay. So we did a full big overlay with our reconstruction techniques were sort of sure at the entire.
And if you run on LX Plus, do you actually do a forward construction?
I don't think that we've tried on LX Plus actually. But from my experience, at least running locally on LX Plus, I know that a lot of those nodes have 60, 32, issues.
Right, so Lincoln, the use case we're talking about the extra memory coming from the old Sonoma school.
I mean, yeah, we can definitely do that. I think in general, if we want to have, large memory nodes, things like that, we just need to start slicing the items so small. Right?
Sure. Yeah, I'll talk more depth.
Yeah.
So in terms of disk usage, without the beam-reduced background overlay, it's not much of a concern whatsoever. We store only about 1 megabyte per event. However, when we introduce this 100% big overlay, just storing the actual simulation hits this up to about 20 gigabytes per event. So you can hopefully see for that those estimations. So in terms of the resources that are actually being used for this, There aren't many dedicated resources with the exception of the OSG, which we've been using for our study. But we also have access to LX Plus, DESI, INFN, and many different analysis facilities at different universities throughout the globe, as well as the Fergie Lab, which is a tool. However, in terms of storage options, this is a bit more limited. As only the OSG and INFN have dedicated storage at the moment. So this can was a bit more of an issue for us. In terms of our data management, this can be a bit complicated as well because we're dealing with many different data formats, whether it be how we encode the geometry of our detector or the different outputs in different steps of the simulation. So it's important that we come up with a method to track all the data formats across the different clusters that we're running. And lastly, in terms of person power, and I'll emphasize that this sort of lack of dedicated funding also sort of underlies many other issues. But this results in sort of a lack of dedicated computing staff for the Muon Collider collaboration, despite dealing with some similar issues, which of course has many more staff. So I'll go over some sort of solutions that have been thought of to deal with some of these challenges, as well as some things that are implemented today. So to deal with the 20 gigabytes per minute background simulation, what we end up doing is just simulating one BIP event worth of files. And splitting these into a large number of files. And then every time we run the overlay, we simply select some random subset of this. So ultimately, we're actually simulating more than one event. That way we can ensure this So this works quite well in terms of conserving storage space. However, we still have the sort of I/O issues. There's also been a lot of thoughts into using heterogeneous computing resources, such as adapting algorithms to be run on GPUs or FPGAs. We think that could likely speed things up quite a bit. And lastly, there's also been thoughts into training machine learning algorithms to actually generate your BIM simulation hits, in addition to the overlay, which we're simulating. At the reconstruction level, something that helps greatly in terms of the storage space of defining objects is to apply some sort of reconstruction level cuts to minimize the number of big objects, such as tracks that I use as an example of that are actually stored in the end. However, that's provides the issue of not being able to best quantify your actual favorites that you're getting with your reconstruction level. We've also tried reconstructing objects only using some sub-detectors at once, for example, just reconstructing tracks, not using data from the cal renders, for example. And this can definitely help with resource usage, but still, for example, in our study, some issues. And lastly, I'll mention that also one reconstruction only in sort of a sub area, tree, using the information you have with objects. That's what reconstruct just what you want from your system. But again, this runs into the issue of not being able to quantify your favorites as well as. But in terms of data management, not many solutions have been put in place yet. But I think there's a strong idea to use Rusio, which is a tool that's quite used in the LHC. And this could provide a solution that can be developed by the community itself based on the experience of Rusio for managing our data sets as well as. Okay, so lastly, I want to talk a bit about my own experience with OSG and using Condor for running this workflow. And I think I'm still one of the only people who Muon Collider study is explicitly using OSG. But I think we hope that more people take advantage of that. But anyway, so I developed basically a workflow to submit Condor jobs on the H23 access points to do our full simulation workflow. However, as I mentioned, we're doing this just at the 10% bit level. So selecting only the fraction of the actual total hits of being used background each event. And to actually use this, we have it so that actual worker nodes can access these already simulated bid files, CDMFS. That's worked fairly well. We also have that we set up our actual environment using singularity. That's pretty well. But ultimately, the issue that we run into with our study, and I think many of the other studies in Muon Collider, is that we want to test more advanced reconstruction. We find that both using more advanced reconstruction techniques and also inputting more bit bits, for example, by extending these timing windows, or how long the detector is actually read out for, this results in requiring significantly more memory. So some challenges that we've been dealing with working on OSG. Again, with the overlay, we require about 15 gigabytes of files per event if you want to run 100% overlay. In terms of reconstruction, as I mentioned, we're dealing with up to about 48 gigabytes of RAM usage with just a 10% overlay. And with some previous tests, we saw that this could scale up by a factor of about 6 times, dealing with on the order of about 300 gigabytes of RAM then, just for processing one event. In terms of storage, we find that our final files that we want to store are about 60 megabytes per event. And this doesn't seem too bad. However, when we take into account that we're running a lot of different reconstruction configurations, and for example, different signal models, this ends up sort of ballooning quite quickly. So some solutions to deal with, especially the memory consumption, was in to use only part of the detector, so only really wanting the track reconstruction. And additionally, we found that processing just one event per job can sort of limit your memory usage. But again, it should probably be fixed that you have this sort of steady increase as you process more events per job. And in terms of storage options, we've been able to take advantage of about 50 terabytes that's available on the OSG for future flight work.
We can bump this to 75.
That would be helpful, yeah.
Right, and the thing is, at the end of the day, for storage, you can even go to 100 for a short amount of period if you have, a campaign to run.
Sure.
Like double the amount. As long as you guys figure out like long-term storage, make some kind of a deal, like Fermi or INFM,
Yeah.
to archive or move the data there, and then keep on flushing the available storage for OSG jobs.
Sure, yeah. Yeah, I think as the collaboration continues to grow, which we hope it will, there'll be more and more studies, but
Russia would actually kind of eliminate some of the issues with individual institutions.
okay.
But we'll discuss the issue option.
Yeah, that would be great, yeah. As I mentioned here, already about half is used up, a lot of which has been done just by a study. So the sort of remaining question for us, which some discussions of some solutions, is how we can actually move up to their use of the not just for our study, but also for others who want to test sort of new configurations, such as extending our timing windows, like with more big cases inputs, and using new more advanced reconstruction points. Okay, so that leads me to some conclusions. Hopefully, I showed that Muon Collider collaboration has many sort of unique computing challenges that's primarily driven by the presence of our use backgrounds, as well as having many different data formats. Hopefully, tools such as resouces, as we mentioned, but has some solutions. On our end as well, I think there's a lot of work to be done in terms of optimizing, especially simulation, overlay, reconstruction steps of things. I think that can definitely lead to some major improvements in terms of especially memory usage, just by afterwards existing builders. But I will say that the OSG, being a dedicated resource for these viruses, has been especially useful for our study. However, again, we're kind of running into a bit of a wall in terms of moving up to now, so we need some sort of not like this remaining issues. And lastly, I'll just mention that I think so machine learning and different heterogeneous computing resources such as gaming computers, for example, but also provide some solutions rather than just needing to scale up. Sure. And I'll say if you're interested in more about the Muon Collider collaboration, I have links to the US collaboration and the international collaboration websites here. Okay, thank you.
Thank you. Questions?
So one way of being able to get to create big on a node is to have a multi-core application.
Sure.
And Xeon does support multiple threads. So
Okay.
if you could go up to 24 cores, then you should be able to hit somewhere. I mean, CMS regularly sends in whole load jobs, and you know, you land on a particularly big machine and it has a lot more than 48.
Sure. Okay.
But you do have to have a multi-threaded application, and like I said, Giantis. So have you tried anything like that?
No, we haven't. And really the issue that we're running into is in our reconstruction algorithms.
Yeah, but if you separate the processes and just have the workflow, you know, use.
Yeah, I don't think anyone has tried that yet, but that's definitely a good idea.
The separation is the problem, right? Because it's part of the framework. The way that we
Yeah.
actually built the framework, we just put it as one big problem. And so instead of breaking into parts, we work just fine. I see what you're saying. It's just that the developers from the framework they have brought this as a inherited from like, I don't know, old Spark Stations machine, I have heard. But they can definitely look for improvement at the development, level.
That's good. Yes.
How much of your problems are solved just by throwing more hardware at it? You know, like if we just gave you a bunch of big memory nodes, you know. How much novel work would you need to do in terms of optimizing things?
So I can speak at least for our study, which is probably at the high extreme of, for example, memory usage. And I think that they would likely be most so nice.
You're smiling, so I don't like that.
Well, it's just like that's a great problem to have, right? You just sit on your hands and wait for hardware to get better.
Yeah, to some extent.
But- Yeah, one thing though, you said you had access to effect. Is it an allocation you had there or storage or what is that?
I believe it's just dedicated storage.
Absolutely.
In terms of.
Okay, so that goes, even if you deploy a issue or storage element there, it's not gonna be useful unless you have some kind of a computing tool, the European side.
Yeah,
So I would urge you guys to find these computing tools. Then you can set up an RFC to these solutions and storage and all. Okay, where you can distribute data.
sure.
And even compute, if you have an allocation of that, and we already have, we do have that points to unplay, right? See? Yeah. So, see, what's from there, but we're very active.
Oh, I'm sure I agree.
I'm sure certainly have some, but I don't know if it's dedicated to the operation and so on. No, it's not open. It's not open. Okay, but I'm sure it will work sometime.
Okay. Yeah, I can relay that.
Any other questions for Mark? All right, thank you, Mark, again.